Hello everyone, I'm Moji, a postdoc at Electrochemical Materials and System Lab, Technical University of Eindhoven. In this presentation, I will talk about topology optimization of porous electrodes for specifically redox flow systems. So redox flow batteries are a promising technology for durable grid scale storage of excess energy coming from renewable systems. And I say it's promising because they have some unique features in comparison to traditional like sealed batteries. And one of these features is actually decoupled power and energy, because in these systems, the energy is stored, the energy capacity comes from the size of the tank that we use to store the electrolytes, but the power density comes from the size of the stack and efficiency of the components of the reactor. So in RFBs, as I said, we have the dissolved species stored in tanks externally, and then it is pumped into the reactor. So in the first place, it comes to the first layer of the reactor is usually considered as a bipolar plate, which we also call current collector. And then on top of that, we have the embedded flow fields in order to distribute the electrolyte evenly inside the electrode. And then we have the porous electrode, which is the main component somehow, because that's where the electrochemistry happens. And then we have a separator that allowing only protons to exchange, and as a result, we can have the charge out of the battery. So this is a very simple schematic representation of the RFBs, but in action, in lab scale or even industry scale, they usually contain more components, such as gaskets, in order to keep everything tight. So in order to increase the cost competitiveness of these systems, one approach can be increasing the power density. As I said, it comes from the reactor design and its components. So we can focus on increasing the efficiency of various components, and we believe that electrode is a performance-defining one because that's where the redox occurs. So in this project, our focus is on tailoring the electrode and engineering it in order to increase its performance. It's both in the hydrodynamics performance and electrochemical performance. And for that, we have also two approaches. One is increasing the efficiency of the surface by tailoring to surface properties, which is more on a chemical side, but we have also one engineering side of this that is trying to optimize the microstructure, the structure in general, and microstructure in specific of these electrodes. So what we want actually from this of these electrodes is what we have. For sure, we need more surface area. We would like to have more surface area. Then it increases the electrochemical performance. At the same time, we want to have boosted mass transport, less pressure drop, because then we can increase the loss that we have or the energy that we need to put into the pump for the pumps to circulate the electrolyte. And of course, we want to have more electrochemical, mechanical, and stabilities for sure. So for doing this, we look at the problem as an optimization problem, as an engineering optimization problem. It means that we can probably do this using an inverse kind of design. And for that, we say that, let's assume that we start with a block of material, and then we perform topology optimization kind of techniques on that. So we come up with non-trivial designs, but at the same time, we also need to consider the next step, that is manufacturing. And we have also some ideas for that. So more specifically, the modeling workflow will be something like this, that we have, as I said, a bulk of material. We can consider that it's the porous electrode is the bulk, and then we have the inlet and outlet. And because you will see this figure more and more in the presentation, you can assume that the membrane is on the top and the current collector is on the bottom face. And then the final the result of this model is something like this, that we have topology optimization results converted to something that we can manufacture. And for doing this, we need actually some steps. The first one is a computational model that can correlate the microstructure and the properties of the electrode to the overall system performance that we want to put as a target in topology optimization. And the next step is topology optimization itself. And then the final step is the upscaling and manufacturability. So I will focus, I will go through these steps quite quickly. So the first step is computational model, and for that, we first need to consider the fact that RFPs are actually highly multi-physics systems. We have that they are multi-scale systems, but at the same time multi-physics. And it means that if I focus on just this part one slice of from one side of the cell to the other side, we will have something like this. And there we have different types of transport phenomena: momentum, mass transfer, charge conservation, and heat generation and transport. So for building the computational model, first we need to have a mathematical framework. So the figure that I showed you, then we can consider different things that we have in a system in the first place as a flow battery. So for sure we have momentum transport that can be nicely described by the Navier-Stokes equation. And then we have mass transport. Mass transport had different actually mechanisms in the flow batteries. So the first one is diffusion. It can be described, by a simple diffusion term in Nair's-Planck equation. It can have reaction, any type of reaction, conversion of chemical species, or something like bottle warmer coming from, electrochemical kinetics, and of course convection. That is the effect of fluid flow on a mass transfer. And then we have charge transport, charge conservation, which can be defined using different forms of equations. This is the really simplest case that we have a simple Poisson equation to describe the conservation of charge. And then when we have charge, we can say that we have also migration, that is the effect of charge on the mass transfer actually. And then we can define different type of kinetics. In this way, we have used the bottle warmer, which is usually the most accepted form of kinetics in this kind of systems. So this is the mathematical framework, and then we can move on and to build the computational framework. For that, we have some simplification for the study that I want to show you here, that we have only half cell of these systems. And then we have 2D and 3D geometries both at the same time. We can consider both for topology optimization. But whenever I show you the 2D geometry, that's actually this diagonal cross-section of the half cell. And then we use finite element formulation to discretize and solve the mathematical equations that I showed you. And at the same time, since we really need high resolution for topology optimization, we need to employ proper solvers, preconditioners, and these kind of things using high performance computing techniques. So that's the computational model, and then in the second component is topology optimization. So I will go through that also quite briefly. So in this case, we assume that electrode is a microporous material. So zooming in a half cell, we can say that we define different representative volume elements, RVEs, inside the electrode, and we assume that it has a constant porosity, but the porosity changes from element to element. And the topology optimization routine actually tries to hit a target for the performance by changing the porosity inside each of these RVEs. And for simplification, for the things that I want to show you, we have skip mass transfer. So we have the fluid flow and the conservation of charge, but this is something that these components can be developed independently, so that's not a big deal to add mass transfer as well. And then we have used the technique of MMA for topology optimization, and the objective function is, as I said before, like trying to minimize power dissipation, which is very equivalent to pumping power loss, and also trying to increase the electrochemical performance. In this case, the target is the charge that is passed through the membrane, one of the boundaries of the system. So in absence of fluid flow, the results are like this. You've seen these kind of shapes probably in topology optimization of reactors. Usually when we have the electrochemical or even chemical reactions, this is a type of things that we have as the output of the system of topology optimization. But if we add fluid flow, then depending on the operating condition, in this case, for example, applied current density or the conductivity of the system or any other parameter, the fluid flow, the fluid actually finds its way through the electrode, either close to the membrane, especially when we have higher conductivity, or from the middle of the electrode, let's say. And then the same type of results we can have in 3D. In 3D, it's a little bit more, let's say, intuitive, because we can say that whenever we have the demand for high electrochemical performance, like we have a higher current density, the material, we need to have some material in between, like in the center of the electrode, but when you increase it, then the topology optimization routine, those mathematical equations, find the best place for the channel to be close to the membrane. So this can be also seen as somehow embedding the fluid field inside the channel, that's inside the electrode, sorry. And then these two phenomena that we're trying to optimize are actually quite contradictory. So whenever we want to improve power performance, power like dissipation, we have actually loss in electrochemical performance and vice versa. So, and it can be seen here. So for different the optimization steps or iterations, let's say, we can see that these two phenomena are actually trying to compete each other, and in the end, the results are a kind of peaceful setup or configuration that these two phenomena have, depending on the operating condition that we have set. And then since these are, the first block was a computational model, we can have also all those parameters that we have in the equations as the output of the topology optimization. So we say when we optimize the structure, then we have certain, for example, current density or ionic electric potential, power pressure drop, and also velocity magnitude, depending on the operating condition. And then the last block, which is also very, very important, is how we want to move on with this. That is, the optimization results, and then so what? So how we can produce them using techniques like additive manufacturing and these kind of things. So the upscaling strategy for us, the idea is we can use periodic surfaces in order to make them. So here is the concept of TPMS structures, triply periodic minimal surfaces, that there are some just equations, some mathematical entities using trigonometric functions that are getting quite popular in mechanical engineering and biological like studies, but also recently in chemical engineering. And the thing is, we can control the features of these surfaces quite simply by changing the coefficients of the mathematical equations. So the challenge here is how we can convert those porosity fields into something that we can produce using the TPMS stuff. And for that, we can take advantage of the concept of distance functions. So we have, as you can see on the left, we have the porosity field converted to volume fraction field, and then we can convert it to distance function describing the distance that each node of the mesh has to the interface. And then on the right, you can see that we have the result, the output TPMS in field that shows that is correspondent to the volume fraction that we have. So whenever we have the low volume fraction, so the blue parts, we have really high porosity in the TPMS, and the opposite on the top right. So if we do this trick on the optimization results for different cases, this is one example of what we can get. So as you can see again, those blue parts are the more porous parts, and the flow goes from the corners of the electrode, and we have more material in the center. And for the case that we have low current density, the result will be like this, where the flow field channel is more towards the membrane, let's say. So yeah, this is the trick, the conversion that happened in the process, and we can, as I said, those blocks, the three blocks that I showed you, they are totally independent and can be developed further to have more results in 2D and 3D, of course. And then another aspect of this work is that all the tools that I use in this different steps of this modeling framework, they are all free and open source, and it means that the workflow is fully reproducible for anyone that is interested in using them. So for mesh generation and multiphysics modeling, later on optimization, and also conversion to TPMS in fields, they are all the tools that we use, they are all open source. So as a conclusion, I showed you the idea here that we can have different blocks in order to start from a porous electrode and then move to the final optimized version of them. So in the first place, we need a numerical model that, as I said, correlate the properties of the electrode to the overall cell performance. And the next place we can plug these models into optimization routines. And then finally, we have also some ideas here for how to upscale and manufacture these results. Yeah, that's what I wanted to say. Thank you so much for your attention.